In this video, we're going to convert the strong form of our boundary value problem. In this case, it's a boundary value problem which models a beam to the weak form of the boundary value problem representing a beam. Let's refresh our memories on how to do that. Remember, when we go through this process of converting from the strong form to the weak form, we start with the differential equation in the strong form, and we're going to multiply both sides of the differential equation by some virtual function. Here, I'm calling that virtual function n of x. In a previous video, I called it v of x, but since our beam problem, we're solving for a function that's called v of x. To avoid confusion, I'm renaming my virtual function n of x. Now, these virtual functions can be any function we want them to be. It just needs to be a function that we know, and therefore we know its values at the boundary of our problem. In this case, the boundary of our one-dimensional beam problem is 0, x equals 0, and x equals L. So as long as I know the values of n of x at x equals 0 and x equals L, I'm in good shape. We're then going to integrate both sides of the resulting differential equation from 0 to L, the boundaries of our domain. We'll then need to apply integration by parts to the integral that appears on the left-hand side of our resulting equation. And then by applying our knowledge of the boundary conditions, we can simplify the resulting equation, and we will arrive at what's called the weak form. So let's go ahead and do that now for our beam problem. You'll remember in a previous lecture, we derived the Euler-Bernoulli equation for beam problems. Here, I've simply taken the Wx, which is our forcing function that represents our distributed load, and I've moved it to the other side of the equation. And here are our four boundary conditions. You'll remember that what we're talking about is that we have a beam of length L, and that the boundary conditions represent the forces and the moments at each end. So we have our F2 and M2, and likewise we have our F1 and M1. And we've also discussed that Wx is a distributed load. In the terms of differential equations, we call it a forcing function, but here it represents a distributed load along the length of our beam. All right, now we've refreshed our memory about what we're talking about. Let's go ahead and take our differential equation and convert it into the weak form. Our first step, again, is to multiply both sides of our differential equation by our virtual function, which I said I'm going to use n of x as a symbol for my virtual function. So doing that, I'm going to get that EI, the fourth power of dv dx, I'm sorry, not the fourth power, the fourth derivative of v with respect to x. Here's my n sub x is equal to negative w x n of x. I'm now going to integrate both sides of this equation from 0 to L. So I will get, since I'm simplifying our case, and we're going to pretend that for now that E and I are constants, or we'll take in our case that E and I are constants, I can move those out, and I can see that E, I, the integral from 0 to L, the fourth derivative of v with respect to x, and x dx is equal to negative the integral from 0 to L wx and x dx. The next step is to apply integration by parts to the integral on the left-hand side of this equation. In this case, I'm actually going to need to apply integration by parts twice. So on this part of my equation, to get terms of the boundary conditions that I want, I'm going to apply integration by parts twice. When I do that, what I'm going to arrive at is EI, the integral from 0 to L of the second derivative of v with respect to x times the second derivative of n with respect to x dx plus EI and then dv dx, the third derivative of v with respect to x times n of x minus dn dx dv squared dx squared. This all evaluated at 0 and L is equal to the right-hand side, which is still from 0 to L of wx nx dx. All right, and I hope you see where this comes from doing integration by parts twice. I've gone from a fourth-order derivative to second-order derivatives, and now I have terms that come from, that need to be evaluated at the boundaries of my domain. What does this buy us? Well, it buys us the fact that I know what these values are at the boundary of my domain. Here is a third derivative of v with respect to x evaluated at x equal to either L or 0. This is the third derivative of v with respect to x at x equals 0 and x equals L. Likewise, I have the second derivative of v with respect to x evaluated both at x equals 0 and x equals L. So using our knowledge of the boundary conditions, I can rewrite this term. Let me go ahead and do that now. I'll rewrite the entire equation, and I will get EI, the integral from 0 to L, second derivative of v with respect to x, second derivative of n, our virtual function with respect to x, dx, plus I have an EI out here. You'll notice in all of these terms with the derivative, I have an EI in the denominator, so that that will cancel out with that EI, and what I'm going to get is terms like the boundary value, the force at node 2 times my virtual function evaluated at L minus m2 times the derivative of my virtual function evaluated at x equals L minus my force applied at node 1 times my virtual function at x equals 0 minus the moment applied at node 1 times the derivative of my virtual function evaluated at x equals 0. And then I still have my right-hand side equals minus the integral from 0 to L wx n of x dx. And now, with this, I have arrived at the weak form of my boundary value problem, where my boundary conditions are now built into my differential and integral equation. All right, so now we've arrived at the weak form. In our next video, we will make certain approximations to both the function v and the functions n, and in doing so, arrive at our Galerkin's method.